Hello friends, I hope you all are well. So today we will be discussing one of the most important theorems in network theory, that is the maximum power transfer theorem. From the previous lectures we have studied about the Thevenin theorem, Norton theorem. In that theorems we have seen that if we have a linear circuit containing only resistive elements and independent sources, we can reduce that circuit into equivalent Thevenin circuit which contains an equivalent Thevenin voltage in series with Thevenin resistance. Or in Norton theorems, we can say that we can reduce that whole linear circuit into Norton current in parallel with the equivalent resistance. So, what if I want to find that what will be the maximum power that circuit will be delivering to the load. So in that case, we can make use of this theorem, that is the maximum power transfer theorem, which is the fundamental concept in the electrical or electronics engineering, which can be used to determine the optimal load impedance or maximum power transfer from the load. So in many applications, in many practical situations, where a circuit where a circuit is designed to provide maximum power to the load. Okay, so like like in, for example, a communication field. Take a communication field where it is desirable to get the maximum power delivered to the load. Okay, so here some problems arises when delivering the maximum power to the load, given a system has some losses internal losses. Why? Because in a given circuit, in any given circuit, we have we don't have ideals elements. We have a practical elements which contains some of the internal losses. Some uh, you can say, like in resistance, we have some internal losses in there. So which can result in significant internal losses, which can greater or equal to the power delivered to the load. Okay, to the load. So let us see what this maximum power transfer theorem says. So this theorem says if we have a power transferred from the supply source to the load at its maximum when the resistance of the load is equal to the internal resistance of the source. Okay, this means that for any maximum active power to be delivered to the the load impedance must correspond to the conjugate of the source impedance. To prove this theorem, we have some cases. So let us move on with that. So we have a case number one, which is the purely resistive circuit containing a variable load resistance. For example, I have this circuit. I have a voltage source, a resistance R, and a variable load resistance RL. Okay. So now the maximum power will be delivered from the source to the load when the load resistance is equal to the source resistance. Okay. So what will be if I find out the current I? It will be V upon R plus RL. Okay, this will be a V plus divided by R plus L according to Ohm's law. So this will be my question number one. Now, what will be the power if I want to find the maximum power? So it will be P equal to I square RL. In this, I want to find the maximum power in this load. Okay, so it will be I square RL. So from equation number one, I can put the value of I, so it will be V upon R plus RL whole square into RL. So here V and R are fixed. Only by varying the load resistance, the power delivered to the load varies. So for maximum power, I can write this equation number 2. What I can do is I can differentiate this. So dP upon dRL with respect to RL, I can equal to put 0. So it will be, when I will differentiate, I can put the value of P here. So d by 1 dRL in bracket V upon R plus RL whole square into RL. Okay, so my V square will be come out because it is a constant. Okay, so V square will be come out, and it will be d upon d dRL into RL upon R plus RL whole square. Okay, so differentiating the using quotient rule, so this will be equal to 0 and this equal to 0. So my V square will go there, it will be 0. This will be R plus RL 4 square upon denominator is 2 square, and numerator, keeping this as it is, R plus RL whole square, differentiating this, so it will be 1 minus, keeping this constant and differentiating this one, it will be 2RL R plus RL equal to 0. Now I will be taking this thing common because it's same values, so it will be R plus RL minus 2RL equal to 0. Okay, this will be get cancelled, one power get cancelled, and this will go there, it will be 0. So it will be R minus 2RL, okay, equal to 0. So what we will be getting, it will be R equal to RL. Okay, so this will be, I will be getting, and this can be question number 3. Okay, now the internal resistance is equal to the load resistance. So what can I do with this? So to find the maximum power, I can put this value of R in equation number 2. Okay, so this will be V square RL upon R plus RL whole square. So by putting this value in this, I will be getting V square RL upon 2RL whole square, and this will be V square RL upon 4RL square. So 1 RL get cancelled, it will be V square by 4RL. So this will be the maximum power which will be transferred to the load, and now I will be calculating, we will seeing the efficiency which is eta. So eta will be equal to maximum power in the load divided by power from the source, which will be equal to I square RL upon I square R. It will be RL upon R, RL upon R, sorry. So this is from the source. So my P source, sorry, R source will be equal to R plus RL. So I'll be putting this value in this, so it will be RL upon R plus RL, and I can put this third from the third equation, I can again put it upon 2RL, it will be half, or you can say it will be 50%. Okay, so I will be getting a 50% efficiency, and what means half the power from the first case. So now this will be, next move on to the second case, when I have a load impedance with a variable resistance and variable reactance. So in this I have a circuit, suppose I have a circuit this V, and I have a reactance R plus J, Jx, and this is at the load R plus RL plus JXL. Okay, this is my circuit. So where V is the voltage source, then this will be the internal impedance and this will be the load impedance. So the same steps, what will be the current? The current will be V upon Z plus ZL, where Z is the R plus load, the internal impedance, and ZL is the load impedance. So it will be V upon, we will be combining the real values R plus RL plus imaginary values J values X plus XL. This will my question number 1. So for maximum power, which will be P equal to sorry, it will be I square R I square RL at the load. This will be equal to B square RL upon only the real, we want only the real value. So this will be this one. You can also do that if we square all this, you can open it and you can verify it. Okay, this will be question number 2. So we want the maximum power. So dp upon dxl, we will first differentiating with respect to L equal to 0, and by doing this, what we will be getting, we will be getting d upon dxl, we will be getting v square rl upon r plus rl square plus x plus xl square equal to 0. So by solving this whole equation, we will the same process, will be getting xl equal to minus x. This will be equation number 3. Means the reactance of load impedance is of the opposite sign, is opposite to the reactance of the source impedance. So this will be putting in, put 3 in 2. Okay, so what will be getting? P equal to V square RL upon R plus RL square plus X plus XL square. This was our equation number 2. By putting this value in this value, so we'll be getting P equal to V square RL upon R plus RL whole square. So again for we will differentiate, but this time we will differentiating with respect to XL, and we are putting 0, which we will getting the same as in case number 1, R equal to RL, and efficiency will be 50%. Okay, so it all depends on the specific impedance involved and their relationship. Okay, so let's move on to the case number 3, where we have a load impedance with a variable resistance and a fixed reactance. So I have this the circuit. In this we have I have a impedance R plus XJX, but this time I have a fixed reactance. This will be R my RL. This will be JXL. Now I will calculating the current will, which is equal to V upon Z plus ZL. The current will be the same as in previous case, R plus RL plus J X plus XL. This will be equation number 1. The power will be equal to V square RL. We have to calculate why we are taking RL. So because we have to calculate the maximum power in the load resistance. That's why we are seeing we are writing RL in the previous cases. Okay, so it will be R plus RL whole square plus X plus XL whole square. This will be equation number 2. So the for maximum power dP upon RL equal to 0. So this will be equal to, if I go on next page slide, this will be V square is taken out common. So this will be why we are not differentiating with this XL first, because X we have fixed reactance. That's why we are not differentiating uh, first with XL. We are differentiating only with respect to RL. So with what will be this equal to? Because using quotient tool we have R plus RL whole square plus X plus XL whole square uh, this will be whole square too. Okay, so first keeping this as a constant, R plus RL whole square plus X plus XL whole square common, and differentiating the next, which is RL, which is 1, then keeping this as a RL constant will be with 2 2 RL. Okay, and with we are doing respect to the XL, though this will be 0, we will be getting R plus RL. Okay, and then equal to 0. This whole thing will get shifted there and become 0. V square gets 0, so we will be getting R plus RL whole square plus X plus XL whole square minus 2RL R plus RL equal to 0. Now taking R plus RL common and shifting there, it will be 0, so R plus, sorry, it will be minus, it will be minus R minus RL plus X plus XL whole square. Okay, I will be getting this. Hmm, okay, I will be getting this. I think I made a mistake here. I'm writing this again. Okay, I think I made a mistake. So I will be taking one thing common, R plus RL square, R plus RL square common. So it will be R plus RL minus 2RL plus X plus XL whole square. Okay, because it will, there was a plus sign. Sorry about that. I didn't see that. So it will be R plus RL into R minus RL plus X plus XL whole square equal to 0. Now this will be a square minus b square. We will use that formula. So it will be r square minus rl square plus x plus xl whole square. This will be equal to 0. And when you take everything there, it will become rl square equal to r square plus x plus xl square. And RL will be equal to under root of r square plus x plus xl square. Okay. Now, if so now if 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 my excess if my excess sorry if my not x, we have taken x, we have taken x. Okay. If my x is 0, then my RL will become r square plus xl square. And if my XL is equal to 0, my RL will be R square plus X square. Okay, X square. And this is equal to nothing but Z. Okay, internal impedance. So what why we are putting X or XL equal to 0? Because I have found out I want to find out the maximum power transfer. Okay, I want to find out the maximum power. So this was the case number 3. Moving to the fourth case, which is the load impedance with fixed ratio. That now we have a magnitude as well as we have an angle. So for angle, let us assume let us assume that angle of load impedance is phi. Okay, so the ZL, that is at the load impedance, what its value, suppose it's a ZL cos phi plus J ZL sin phi. Okay, so the power delivered will be V square XL cos phi. Okay, divided by, because we only want the real values, so it will be X plus ZL cos phi whole square plus X plus ZL sin phi whole square. Okay, this is number 1. So it will be the for maximum power dp upon ZL, because we don't have RL. We have to find only in load impedance. That's why we are differentiating with respect to L. So what will we be getting? We'll be getting ZL square equal to RS square. Sorry, my old habit. It will be R square plus X square, which will be Z square, ZS, you can say. So it will be ZL equal to ZS. Means this is the case where in a transformer where the turn ratio is varied for the maximum power transfer. Okay, so this was the cases we have considered when we have given we have a circuit when we have to find out the maximum power in the load impedance or in the load resistance. Okay, so let us understand this whole theorem by this numerical problem. So in this circuit, I have to find the value of RL, and after finding the value, I want to find out what is the maximum power in RL. So to find out, first of all, what we can do is we can reduce all this using the Thevenin theorem. Okay, so for that, what we have to find out, we have to find out the VTH and R equivalent. So first of all, let's calculate for the R equivalent. What we have to do that for R equivalent, deactivate these two sources and remove this RL. So what this circuit will be looking like, this will be the short circuit. Okay, this will be resistance, this will be open circuit my when current source is moved, and this will be my after removing the load resistance. This is 6, 12, 3 and 2. So to calculate the R equivalent, okay, this 2 is in the series, so it will be 6. Sorry, it is in the parallel 6 or parallel 12, and this 2 is in the series because this is A current source is now open circuit, no current going, so this will be in series, so this will be equal to 5. So my R equivalent will be equal to 9 ohm. Now my once R equivalent came, so we have seen from the previous case, in the four cases, that my R equivalent or internal resistance is equal to the load resistance. So that means my value of RL will be 9 ohm. So my RL came. For my maximum power, I want, for Pmax, I want VTH upon 4 VTH square upon 4 RL. Okay, the first case. So I want VTH. So how will I be calculate? You can use deploy any method like mesh current, nodal. Okay, so I will be using nodal here. I'm using nodal analysis. So for that, my circuit will be this one, 12 volt. This will be my 6 ohm. This will be 12 ohm, 3 ohm, 2 ohm, and here 2 ampere. Okay, for that, first we have to remove the load, and by watching from here, I want VTH from here, that is the source, open circuit voltage. So what will be I be seeing from this side? My this is VTH, my this is VTH, because there is no current going on, so I can add this VTH, and this will be my VA. So I'll be writing directly the equation of VA. Okay, I'll be writing, so by using the nodal, I can write this. I can I can assume this is the ground. So VA minus 12 upon 6 plus VA upon 12 plus VA minus VTH upon 3 equal to 0. Okay, from here my VA will be 1 by 6 plus 1 by 12 plus 1 by 3. Okay, my plus VTH 1 by minus 1 by 3 equal to, it will be 2. 12 minus 12 by 6 is minus 2, it will be there. This will be equation number 1. Or you can also simplify it. We can get VA 7 VA upon 12 minus VTH upon 3 equal to 2, and this will be getting by when solving is VTH minus VA upon 3 equal to 2, or VTH minus VA equal to 6. This will be my equation number 1. This will be my equation number 1. Oh, sorry, I made a mistake. So when we will be solving this one, so you will be getting 7 VA minus 4 VTH equal to 24. This will be equation number 1. Sorry, I made a mistake. That was my blunder mistake. So our this thing is done. Now from here, the VTH value, we write equation for VTH. So VTH will be VTH minus VA upon 3. There is no current going on. It's open source, so there will be no voltage, no current. So it will be equal to, now where this current, it will be 2. Now this is equal to 2. So simplifying this, we have VTH minus VA equal to 6, or VTH equal to, or you can say that I can write VA equal to minus 6 plus VTH. Okay, this one equation 3. Now putting 3, put 3 in 1. When we will putting the value of VA, we will be getting 7 minus into meter 6 plus VTH minus 4 VTH equal to 24. It will be minus 42 plus 7 VTH minus 4 minus 4 VTH equal to 24. This will be 3 VTH equal to 24 plus 42. 3 VTH equal to 66. So VTH value will be 22 volt. Okay. So I got VTH, I got RL. Okay. So my power transfer will be VTH whole square upon 4RL. That will be equal to 22 whole 22 square 4 into 9, which will be come out to be 13.44 watt. So this will be the maximum power my source will be transferring to the load. So I hope you understand how this maximum power transfer theorem works in solving a numerical problem. So and to conclude our today's lecture, you have to remember some points. First point is it is to be noted that when the maximum power is to be transferred, it only transfers half of the applied voltage which is available to the load and other half drops across the source. So this is useful. This will be this thus the useful maximum power will be less than the theoretical value which is delivered and will depend on the voltage required to be maintained at the load. As for the second one, for circuits having a resistive load being supplied from a source with only an internal resistance, the maximum power will be transferred to a load when the load resistance will be equal to the source resistance as we have seen in the first two cases. So I hope you understood today's lecture, the maximum power transfer theorem. If you have any doubt, you can tell us, you can ask us in the comment section. And if you like today's session or today's lecture, so please give a like to this video, comments if you have any doubt, and share this video with your friends and please it is requested to subscribe our channel and press the bell icon so that you can receive the notifications in the future. Till then, thank you very much.